Hey guys, how you doing? This is Coach Scott with another edition of Purple Wave Chemistry, and today we're introducing, doing a pre-lab, if you would, prior to our, what I like to call ICY Hot Lab. Now in this lab, we're going to take a beaker of ice and we're going to heat it up with our temperature probes until it melts. Then we're going to keep heating it until it changes into water vapor, otherwise known as boiling. So what we're going to see here, and if we were to draw a temperature time chart, so that's our temperature, and here's our time. Okay, we know some things. We know, or we assume, rather, that the freezing point, or the fusion point, if you would, of water is 0 degrees C. So we're going to put that point right there, 0 degrees C. And we all also been told that our boiling point of water is 100 degrees C. So if we go from ice, 0 degrees C, to boiling water, we're not going to have a straight line. We're going to have something different. So what we're going to see in our lab is we're going to see a plateau, if you would, where we're adding energy from the heater, but it's going to be pretty flat until all the ice is melted. Now we'll have water in there and ice, but the energy that we're adding is not thermal energy, it's phase energy. We're adding that energy in there to break those attractions that are holding those molecules together. And then after all the ice is melted, then we'll start to see an area of temperature increase. And it'll gradually increase till we get to the boiling point. Then it's going to plateau out again until all the water has boiled out. So we have a low temperature plateau, an area of temperature increase, and a high temperature plateau. So what we're seeing here is we're seeing what's going on with the molecules in this graph. So in the ice, okay, we've got attractions that are holding these molecules together. And as we add energy in there, and this is why it's flat, all of this energy that we're adding is going to break these attractions of these molecules to each other. And now this one, this water molecule, is able to flow around and do its thing that it wants to do. All right. So something similar to this model, right, is going on here. As we grab a bunch of these little water molecules here, they're water, they're liquid, they're able to move around, they can rub against each other, they've got fluidity, they're rotating, whereas when they were in the solid matrix, there was no rotation. They couldn't because they were so attracted to each other. Here, they're not as attracted, but as they start to heat up and we get closer to the boiling point, they're starting to move further apart from each other because more energy is added to them. There's more velocity, there's more collisions. And so as more energy is added and we get to the boiling point, these molecules are now able to separate themselves from the liquid water, and now they're able to move around a lot. They can rotate. There's lots of things going on now. They're gas, so they're going to act like a gas because they are a gas, right? And that's why what we saw with the little bubbles coming from the water was water vapor, water gas inside of these little bubbles escaping from the liquid and going into the atmosphere. Now next, I'm going to show you the math like we normally do on what's going on inside of this curve. Again, there's no temperature change here or there, all right? There is a temperature change there, and that's going to be very important when we start to do the quantification of the energy that's being added into this system. Hey guys, how you doing? Coach Scott again, back at the home studio. So I'm going to break this video down into two parts because they're pretty long. So we described what we did in the previous scenes, and now on our next video, I'm going to do the math, the quantitative part of what's going on. So hopefully you'll join us for part 2 of this video. Thank you so much, and hullabaloo, commit.